All right, so I had reacted to a video of Sabine where she had talked about dark matter and a potential theory, and ShawnS07 responded to me saying that, in his opinion, I guess, dark matter is dilated mass. So I'm just going to jump down that rabbit hole and see where this leads to.
The mountains.
And
Yep.
yeah, starting with an ad. Cool.
Dark matter has been theorized to explain the abnormally high rotation rates of stars in spiral galaxies.
Yeah, this is a good demonstration over here. So given our mass, we expect it to rotate much slower than it actually does. And given how fast it rotates and given the mass that we can see, we expect it to just fly apart, but it doesn't. So that's where the assumption of a dark matter or missing matter or some sort of mass or some sort of change in physics is needed. So we don't even have to go very far from our neighborhood, just within the galaxy. We see these anomalies in known current physics.
There must be far more mass than what is visible to explain this phenomenon. The explanation has to do with what exists at the center of galaxies. Mainstream thought today is that singularities, black holes, exist there. Most people don't know that Einstein said that singularities are not possible. In the 1939 journal Annals of Mathematics, he wrote,
Well, I'm not surprised, but there's a lot of things Einstein said that, he didn't like quantum physics either. God does not play dice with the universe and all of that. But, just because someone makes a breakthrough doesn't mean they're right about everything. So, but it's interesting. So,
the essential result of this investigation is a clear understanding as to why the Schwarzschild singularities. Schwarzschild was the first to raise the issue of general relativity predicting singularities do not exist in physical reality. Although the theory given here treats only clusters, star clusters, whose particles move along circular paths, it does seem to be subject to reasonable doubt that more general cases will have analogous results. The Schwarzschild singularities do not appear for the reason that matter cannot be concentrated arbitrarily, and this is due to the fact that otherwise the constituting particles would reach the velocity of light. He was referring to the phenomenon of dilation, sometimes called gamma or Y. Mass that is dilated is smeared through space-time relative to an outside observer. Even mass that exists at 75% light speed is part.
So, the way that pop science and other people think of this is there's a singularity. Oh my God. Our physics predicts a singularity, our physics predicts this, either it's wrong or right. The way I view it essentially is that it's a singularity, and a singularity is where the current model, this current physical model breaks down. And so it's an indication that there's a deeper model of physics that's waiting to be discovered, which within limits satisfies general relativity, and within other limits satisfies quantum mechanics, and so on and so forth.
Partially dilated. Time dilation is just one aspect of dilation. General relativity does not predict singularities when you factor in.
I'll be honest, I have not touched special relativity or general relativity in like over 20 years, maybe 30 years. Oh shit. So instead of just reading this and watching it on my own and trying to make some smart aleck comment, I'm just going to jump down the rabbit hole and just be honest about it. So I had actually forgotten that there was such a thing as mass dilation. So right now I'm just trying to refresh my thinking.
In dilation. Einstein is known to have repeatedly spoken about this. Nobody believed in black holes when he was alive for this reason. Wherever there is an astronomical quantity of mass, dilation will occur because high mass means high momentum.
No one believes in black holes. This he was arrived. Yeah, I don't know about that. They did see the bending of light in a solar eclipse. So, I don't know.
There is no place in the universe where mass is more concentrated than at the center of a galaxy. It can be
Again, saying no one believed, it's kind of, a very blanket statement. So, could be there were a few people who believed. I don't know, but generally maybe they did not.
shown mathematically that the mass at the center of our own galaxy must be dilated. This means that there
Yeah, I'm sorry. When I start going into physics and videos like this, I get very pedantic with respect to limits and known and unknowns, because otherwise you get into big trouble bigly fast.
is no valid XYZ coordinate we can attribute to it. You can't point your finger at something that is smeared through space-time, or more precisely, everywhere you point is equally valid.
Right, so there's something magical about the speed of light in special relativity and general relativity that effectively causes this infinity and 1 over 0 and all of those things. So mass gets distributed everywhere if you're at the speed of light.
Galaxies with very, very low mass or low mass in their centers do not have enough mass in their centers to achieve relativistic velocities. Therefore, they do not contain dilated mass.
Okay.
To date, 5 very, very low mass galaxies have been confirmed to show no signs of dark matter.
So NGC1277, let's do some fact checking. NGC-1277. Would it be nice if they actually provided a publication? So NGC1277 is a lenticular galaxy in the constellation of Perseus. It is a member of the Perseus cluster of galaxies and is located approximately 73 megaparsecs, or 220 million light years from the Milky Way. Just a reminder, a light year is how far light travels in 1 year. So it takes 220 million years for light to get from NGC1277. I mean, even this sort of things, like when you think about it, the light that we're looking for, the light that we're looking at, that we identify NGC1277 with, the light that we use to identify the galaxy is 220 million years old. That's insane. So, what the galaxy is right now is we're looking back in time by 220 million years. Anyway, it has a magnitude of about 14, apparent magnitude of 4.7. It was discovered December 4, 1875 by Lawrence Parsons, 4th Earl of Ross. 1875, it's a long time ago. Has been called a relic of the early universe. Due to its stars being formed during 100 million year interval about 12 billion years ago. Wow. Stars were formed at a rate 1,000 times that of the Milky Way galaxy's formation rate in a short burst of time. So just browsing through, you looking for the mass. Initial observations made using the Hobby Eberly telescope at Texas's McDonald's Observatory suggested the presence of a black hole with a mass of about 1.7 times 10 to the 10 m dots, which is 17 billion solar masses. So m dot, I guess, is solar mass. So 17 billion solar masses, equivalent to 14% of the total stellar mass of the galaxy. Okay, so 14% of the stellar mass of the galaxy is in the central black hole. Due to the motions of the stars near the center of the galaxy. Okay. This resulted in the initial claim that the black hole in 1277 is one of the largest known in relation to the mass of its host galaxy. Okay, so originally they said that the black hole was very big. A follow-up study based on the same data and published the following year reached a very different conclusion. The black hole that was initially suggested at 17 billion solar masses was not as massive as one thought. The black hole was estimated to be between 2 and 5 billion solar masses. Oh, so not 17 billion, only 2 and 5 billion solar masses. This is less than a third of the previously estimated mass, a significant decrease. Models with no black hole at all were also found to provide reasonably good fits to the data, including the central region. Oh, okay, so after using stellar dynamics and luminosity models to estimate the mass of the black hole, they came to a mass of 4.5, I guess 0.5 billion or 500 million solar masses, similar to the estimate from the follow-up, which estimated a mass between 2 and 5 billion solar masses. Huh? Oh, okay, 5 billion, okay. More recently, a new group made observations using the Larger Keck telescope with superior spatial resolution, calculated the black hole with a mass of 1.2 billion solar masses fits best. Okay, so it is a small galaxy. So I'm just going to take his word for it. I'm just going to take your word for it.
The missing mass needed to explain the abnormally high star rotation rates in galaxies is dilated mass.
Okay, so essentially this video is saying that for smaller galaxies, you don't need any dark matter. For galaxies that are small enough to not have relativistic effects at the center of the galaxy, you don't need dark matter. Whereas galaxies that do exhibit relativistic effects in the center, I guess the proposal is that you could use mass dilation and not need any extra matter or any extra particles. Which is a fair thesis. I'm just curious if there's any math behind it. It would have been nice if they showed the math. And so that's when I sort of started to wonder, okay, what is relativistic mass? So let's see what Fermilab has to say. I'm sure it's going to be fairly authentic given it's Fermilab. It's 7 years ago, but let's see. Fermilab, US Department of Energy.
Without a doubt, Albert Einstein's theory of special relativity makes some very mind-blowing predictions. Clocks run at different rates, objects shrink, and things can't go faster than light.
Right.
And all of these things are absolutely true. Relativity has been thoroughly tested, and there is no credible criticism of the theory, although you wouldn't know it from the piles of unsolicited correspondence I get on the subject. So let's talk about that last one. The idea that you can't go faster than the speed of light. This is a well-demonstrated fact.
Well, I would say within our current known limits, for most of what we can observe, it's true. Relativity is true. I would not ever say that relativity is not true, but I am open-minded to the possibility that there's something beyond relativity. So where it is possible to go faster than the speed of light, where it is possible to travel instantaneously, I'm open to everything. We just don't know what we don't know. But within current limits, relativity has held pretty well.
So why is it true?
Well, it's held up exceptionally well.
If you ask a well-educated scientific layperson, they will tell you that it's because the mass of an object increases as the velocity increases. In fact, you'll hear this said by people with physics degrees. There's only one thing. It's just not true. Now, I realize that me saying that is going to confuse a lot of you, like this guy here, for example.
Right, okay.
So what's going on? Why is it that even some physicists will say that the mass of an object increases as the speed increases? Heck, why is it that even I have said that upon occasion? Shh, don't tell anyone. The reason is a combination of how scientists teach relativity and our intuition at low velocity. I'm going to explain it to you first conceptually and then show just a little math for the physics-minded viewer. So it starts with the concept of inertia. Inertia is the property of matter which resists changes in motion.
Right.
Basically, it's equivalent to the idea that I can push this toy car easily, but this much bigger car is harder to push.
Right.
And at low speeds, inertia is equivalent to mass.
Right.
At very high speeds, this is no longer true. Mass and inertia are no longer the same. An effect that didn't matter before begins to matter a great deal.
Okay.
So this is where it is easier to show what is going on with physics equations. I know some of you have equation anxiety, but don't worry. I promise I'll be gentle.
So look, guys, I'm going to take credible videos at their word for the most part, based on my intuition, having studied physics, having done well in undergraduate and in grad school. But if you don't have a physics degree, I would highly recommend you using these videos as, if you're interested, as incentive to go in and read up on the actual theories in the physics. So I will be taking shortcuts through this video and just taking people's words at what they're saying and seeing if I can find a simple way of, weighing how credible their thesis is. But if you don't have a background in physics or you haven't studied advanced physics, I would say use this as motivation to dig up the actual theory.
If you've ever had a physics class, you've encountered a concept called momentum. Momentum has a meaning very similar to the colloquial meaning. Colloquially, once something has momentum, it's hard to stop.
Right.
Well, in physics, we write momentum using this simple equation here.
Right.
P stands for momentum, M stands for mass, and V stands for velocity. So you see, momentum can get big if mass is big or if velocity is big.
Right.
Or, I suppose, if both get big.
Right.
Momentum is related to inertia. Something with a lot of momentum is hard to stop. But that could be a slow-moving but very massive train, or a very light but super fast bullet.
Right.
That equation and those intuitions are pretty familiar.
Yep.
The problem arises when we start going at speeds that are very fast.
Right.
At very high speeds, this equation no longer applies.
Well, it's
The
modified.
correct equation is this one here.
Right.
We see that it looks like the normal momentum equation, but there is this
See, again, it's like you need to, within limits, go from one model to another. So in relativistic speeds, so that equation always holds, but if you're not at relativistic speeds, just gamma goes to 1. So it's not contradictory, it's just you move to a different regime and you never need to consider gamma for most, I guess, real-world situations.
added term, the gamma term. In fact, this equation with the gamma term is really the right momentum equation, and it works just fine even in day-to-day life. So I told you that the equation for momentum was P equals m times v, and also P equals gamma times m times v.
Right.
How can they both be true? That's because at pretty low speeds, gamma has a numerical value of 1.
Oh no.
Think about some really fast things. The fastest fastball ever thrown, gamma is about 1, or more specifically, this number here.
Right.
How about a bullet from a sniper rifle? That's pretty fast, but gamma is still pretty close to 1.
Yep.
This time, it's this number here.
Okay.
In fact, in order to make gamma to be 1% different from 1, which is to say 1.01, you need a velocity so fast that it can circle the Earth at the equator in a single second.
Wow.
So in any situation you've ever encountered,
It's a really good explanation. I'm really pleased with this so far. Really good videos. So it seems that the further back you go in time, the better the quality of the videos are.
Gamma is basically 1, and you can just drop it from the equation.
Right.
But when you start going very fast, you can't do that anymore.
No.
At 10% the speed of light,
Yep.
gamma is 1.005.
Yeah.
At 50% the speed of light, gamma is 1.155.
Oh!
And at 90% the speed of light, gamma is 2.294.
Shaky.
When you get to
Right.
99% the speed of light, gamma is 7.089.
Yeah.
And as you get even closer to the speed of light,
Right.
gamma gets bigger and bigger. As you approach the speed of light, gamma becomes infinite.
Mm-hmm.
The equation here on the screen is how you calculate gamma.
Right.
The symbol V is velocity and C is the speed of light.
Right.
I just put it here if you want to play with the numbers yourself. If you don't care to do that, you don't need to worry about it, but I know some of my viewers really do love their equations.
Right.
So let's get back to the idea that mass increases as you go faster and
Thank you. I appreciate the equation from 7 years in the future.
faster. How did that arise? Well, basically, it boils down to how we physicists introduced relativity to new students. Almost all people who are learning about relativity have taken an introductory physics class, and they're very familiar with the classical momentum equation.
Right.
So what physicists did was to invent an idea that they called relativistic mass.
Relativistic mass.
Relativistic mass was just gamma times the actual mass. If you do that, you can then write the momentum equation as just momentum equals relativistic mass times velocity.
Right.
That equation looks just like the introductory momentum equation. Taking this approach is helpful when you teach relativity.
Yeah.
That way, you can focus your lesson not on new and unfamiliar equations, but rather on big ideas, especially the idea that momentum at high speeds acts differently than it does at low speeds.
Right.
But this idea of relativistic mass comes at a price.
Right.
The price is a misconception.
Okay.
For instance, people might take relativistic mass and Newton's equations for gravity and come up with some silly hodgepodge equations that don't accurately reflect what is going on. For instance,
Oh, okay. So he's actually talking about relativistic mass. So F is equal to G. So I think this is actually getting into. So this is the gravitational force. The force is equal to gravitational constant, mass of the first object times mass of the second object, divided by the square of the distance between them. And so he's specifically saying that using relativistic mass to calculate the gravitational force is nonsense, according to him. So, but again, much like Max Planck, if you get the result, then there's more to think about. But let's see what he has to say.
For instance, if a particle moving very, very close to the speed of light has a near infinite gamma, I've had people tell me that this means it has an infinite mass, and such a particle passing near the Earth will have an infinite force.
Oh, right.
This isn't true, but it confuses the heck out of some people.
Right.
Now, I should be honest and admit that there is some debate in the physics community about this relativistic mass idea. For those of you who want to dig into this whole thing a bit more, I've put a URL in the description for
The concept of mass in the Einstein year. What? Various facets of the concept of mass are discussed: the masses of elementary particles and the search for Higgs, the masses of hadrons, the pedagogical virus of relativistic mass. Virus? That's harsh.
for this video that gives you something to read. But I would have to say that the majority of physicists who deal with relativistic situations on a daily basis really dislike the concept of relativistic mass. We say that an object has only one mass, which is the mass you measure for an object when it isn't moving with respect to you. Some people call that the rest mass, but it's really the only mass. So I suppose that on behalf of physics educators out there, I should apologize for this confusing concept. Relativistic mass is a great way to develop intuition on why you can't go faster than the speed of light. After all, if mass gets infinite, it gets harder and harder to push it.
Well, they kind of, okay, so they kind of absorbed gamma into mass and that led to confusion. But if you leave gamma outside of mass, you still have gamma, and you still have the equation that says that momentum is equal to gamma times regular momentum, and as you get close to the speed of light, the momentum grows randomly. And so, I mean, that is kind of weird, right? It's like the faster you go, the higher the momentum is. And if the idea is that this is mass dilation, that the mass is in multiple places and you're trying to relate it to inertia, so it's harder to stop because you need more mass to stop it. So you need more force to stop it, and you need more force. So this is where the physical intuition gets a bit fuzzy. You need more force to stop it according to the original video because the mass is dilated, it's spread out. I mean, why would you need more force? You need a larger surface area to stop it. Yeah, so the intuition behind gamma is tricky.
So it has some pedagogical value. But if I may be permitted a biblical reference, there comes a time when we must put aside childish things.
What?
And relativistic mass is one of those things one must move beyond if you want to really understand relativity. Of course, this leaves us wondering why we can't go faster than light. Without relativistic mass, we're left with a momentum equation which tells the story, but really doesn't develop your intuition. So I'll tell you what, I'll make another video that explains the real reason that you can't go faster than light.
Yeah, look, this is not wrong. This is not like, he's just staying within the realm of special relativity or relativistic physics. And for someone that's spent their entire life, delving deep into it, and this is all they've seen, they make a shortcut of saying this is physics, this is reality. But yeah, I mean, within the realm of known physics, I mean, the point of science is to always leave the door open to new science and new discoveries and new theories. Let's see, mass dilation. What is mass dilation? By iTutor from 4 years ago.
Hello everyone. Today we're going to be talking about mass dilation.
Okay.
We've learned already about time dilation and indeed length contraction.
Right.
But mass dilation has the advantage of the fact that it's
So time dilation and length contraction. Essentially, when you move close to the speed of light, or at close to the speed of light, then I can't remember which is which. It's been a while, but according to the observer that's stationary versus the observer that's moving, which in special relativity you can't really tell which is which. They're both valid frames of reference, but the other person seems to have time dilation. You seem to experience time dilation, and the other person appears to have length contraction. It appears that they're shorter than they actually are. Stuff like that. It's weird. It's cool, but weird.
It's one of the events that we can regularly observe in things like particle accelerators.
Uh-huh.
And so in these large machines that accelerate tiny particles to almost the speed of light, we can notice mass dilation as they move very quickly.
Okay.
So, how do we get to mass dilation? We start off with momentum, right? Because momentum is a quantity that depends on velocity and it depends on mass,
Right.
right? So it seems a good way to tie in.
Is he going to
Now we
repeat
know
the same
that
stuff?
momentum is conserved in collisions, right? It turns out that even if we go down to a very, very small scale and we look at individual atoms, we can still see momentum being conserved, no matter how fast they're moving. So we're going to assume for the moment that the conservation of momentum will always remain the same, even if we're traveling at relativistic speeds.
Right.
right? Now, according to the principle of relativity, the laws of physics cannot change depending on how fast you're going, right? You can't see a physical law like conservation of momentum be violated just because you're moving fast.
Right.
So what this means is that if we notice anything odd happening to conservation of momentum, we're going to have to change how we think about momentum.
It's very slow, but I'll be
to demonstrate
patient.
A little example of how that momentum can change, we're going to be doing a thought experiment.
Okay.
Except we're not going to be using a very fast-moving train.
Mm-hmm.
We're going to be using a collision between two spacecraft.
Mm-hmm.
Just because this experiment is a little hard to think of if we only use trains.
Mm-hmm.
So, here we have a short animation showing us two spacecraft coming close to each other and colliding. Right?
Right.
So, we say that the spacecraft are of equal mass,
Mm-hmm.
and they're approaching each other at the same speed.
Okay.
Right? And we can see that they're rebounding a little bit afterwards.
All right.
Now, when they collide, we can see that they start moving away from our line in the middle.
Right.
Right?
Right.
So it means that after the collision,
Right.
each one of them has a component of motion in the y direction.
Right.
And of course, if we conserve momentum,
Mm-hmm.
then the component of motion will have to be the same for both.
Right. Okay.
We can say that it's 10 meters per second.
10 meters per second. Lobbly chobbly.
Right?
All right. All right, mate. All right.
We can say that the collision doesn't affect their direction in the x direction very much. Right? So we can say that their velocity in the x direction is about the same.
Mm-hmm.
Make sense? We can see that their velocity in that direction isn't really changing very much, especially if they only gain that amount of speed each way.
Mm-hmm.
Now, let's suppose that instead of looking at it from this point of view,
Right.
where the ships are moving toward each other at equal speed,
Okay.
we look at it from the point of view of one of the ships.
All right.
Now, this means that we're going to be starting to travel at relativistic speeds instead of being stationary. What this means, though, is that our definitions of meters and seconds are going to change. So we'll see what happens to these speeds.
The fact that he's writing on a board with the projector on top of it is making me a bit nervous. I don't think it's going to be a great presentation, but let's see.
Going up and down, shall we?
Oh, that's what you're going to do.
So,
All right.
let's go into the frame of reference of the bottom spaceship.
All right. Let's do so.
So now, as you can see, we
Right.
start off as stationary.
Okay.
Now, if we look at what the first observer saw when the spaceships
Right.
collided, we know that after the collision, we're moving down at 10
See, length contraction. The other spaceship appears to be shorter.
meters per second. Right? This makes sense?
Sure.
We can see that the x velocity
Right.
of this moving spacecraft is going to stay around the same.
All
So
right.
we've got momentum conserved in this direction.
All right.
Starts off high to the right, ends up high to the right.
All right.
But how fast will this be moving upward, given that we know about length contraction and time dilation? Well, we don't need to worry.
Well, it's a very small speed in a tangential direction. Interesting.
Worry about length contraction. Sure, we're moving upward, but we're moving upward at such a slow speed, probably.
I mean, conservation of momentum, so the momentum has to be the same, 10 meters per second.
that we don't need to worry too much about the distance changing. What we do need to worry about is the time changing. Because now that we're inside this frame of reference, our seconds are going to be a different length to the first frame of reference. So if the first frame of reference says that this ship is going up at 10 meters per second,
Right.
how fast is it actually going up? Well, we can use time dilation, right? So if the observer is moving at 0.6 c relative to us, then one of their seconds turns into 1.25 seconds. So this ship isn't moving up at 10 meters per second, it's moving up at 10 meters per 1.25 seconds.
Right, so it's 10 over 1.25.
And
8
of course,
meters per
10
second.
divided by 1.25 gives us 8.
So that's the velocity, not the momentum. Sorry. So he said the velocity, right? So there has to be conservation of momentum, but since this is identical, right? So he knows that in the frame of the other spaceship is moving at the same, because it's a symmetrical situation, identical. The other spaceship perceives itself as moving at 10 meters per second. So in order to convert their reference frame into the reference frame of the bottom spaceship, you take the 10 and divide by 1.25, accounting for time dilation. So in the bottom spaceship's frame of reference, it observes the top spaceship moving away at 8 meters per second from a constant frame according to it. And then he's going to say, because of conservation of momentum, that means that the mass appears to be dilated. But from the previous video, they say that's the gamma factor.
Meters per second. Hello, now we have a problem.
Okay.
We've said that the x momentum is conserved, right? Because that pretty much doesn't change. But now, we've got two spaceships of equal mass.
Right.
One's going down at 10 meters per second.
Right.
One's going up at only 8 meters per second.
Oh no!
So it looks like our momentum has changed.
Okay.
So how do we explain this if we still want to keep conservation of momentum?
Well, it's a gamma, right?
Well, we can't change the velocity.
Uh-huh.
But what else does momentum depend on? That's
Okay, so we already know as gamma, he's going to call that the mass dilation, but okay, let me just do a shortcut over here. Intuition for mass dilation. You're the relativistic mass. I've seen this guy's face. 50,000 views. Right, so gravity is the curvature of space-time. Oh, okay, so gamma is essentially you are creating curvature. Let me think. Oh, you're creating curvature. Dude, this is relativistic mass and energy. Let's still see. Understanding mass increase. 1,000 views. Let me see. Professor Dive, mass energy equivalence. That's an easy one. Time travel is possible. Is relativistic mass real? Or is this a different one? No, it looks like the same one, right? From Fermilab. Uh, oh, this one looks interesting, so I might come back to it some other time, but levels of complexity. Physics 62, special relativity, relativistic mass. Michael van Biesen. Michael van Biesen. Arthur van Biesen, eh?
Now let me begin by even just writing it down for you, then
All
we'll
right.
explain it. So it says that the relativistic mass is equal to the mass of an object with a little zero on the bottom. That means the mass of the object at rest. This is called the rest mass.
Yeah.
And there's an additional factor, which is 1 over the square root of 1 minus the velocity squared of the object divided by c squared. And for those of you who've been following along in previous discussions, you will know that this is the gamma factor that crops up all over the place in the special theory of relativity.
Right.
And the key part of this equation is that you see that the relativistic mass depends on v, on the speed of an object. So the first thing that I want to do is try to give you some understanding of why in the world you'd ever suspect that there's a use.
Okay, I don't think they're gonna answer anything but mass, dilation, dark matter. So we already saw that one. Can we find dark matter? Amazing ways to look for dark matter. Is relativistic mass real? Did I just prove dark energy is an illusion? Dark energy and dark matter are two different things. New explanation for the something terrifying existed before the Big Bang. Okay. Is dark matter just relativistic mass? Okay. Yeah, I saw this one. So
Hello wonderful person, this is Anton, and in this video we're going to discuss a relatively new proposition that tries to abandon the idea known as dark energy and instead focuses on something entirely different.
oh dang. Okay, there's dark energy.
Dark matter.
Yeah.
Dark matter is a mysterious substance that makes up about 85% of the total mass in the universe, but it does not
Right.
interact with light in any detectable way.
Okay.
Its existence was first proposed to explain the surprising behavior of galaxies. They rotate much faster than expected based on their visible mass alone,
Right.
without the additional mass provided by dark matter. The gravitational force would be too weak to hold galaxies together at those speeds, and they would tear apart. Dark matter doesn't emit, absorb, or reflect light, making it invisible and hard to detect directly. Its presence is inferred mainly from its gravitational effects on stars, galaxies, and large-scale structures in the universe. The leading candidates for dark matter are theoretical particles, such as WIMPs, weakly interacting massive particles, axions, or other exotic particles that haven't been discovered yet. Scientists use indirect methods like gravitational lensing, where light is bent.
Okay, so the idea is growing on me. I mean, as far as the model is concerned, I think let's see if they actually simulate a model with, I mean, what's the physical intuition behind, so this is where you would want to push through in terms of thinking of ideas is, all right, you're talking about, let's say, mass dilation, right? You're proposing a concept of mass dilation, and what you're proposing is that the mass is widely distributed when you get to relativistic effects or scenarios. And in that case, you would want to draw up a model and simulate the model and see if your model does project the expected angular momentum or rotation speed of your galaxies. And from what I'm seeing, there's no model as such. They're just sort of saying like, oh, it can be, this is the explanation. And so it's a little bit underwhelming. I mean, conversely, they're just saying like, well, you know, the gravitational force is m1 m2 over r squared times g. And if your m1 is a relativistic scenario, then you have an increase or a mass dilation or an apparent increase in mass, which, you know, does that equate to an increase in gravitational effects? That's a different question. The other question is that if it's more spread out, my intuition is that, well, some of the mass is closer, and so, you know, that part of the mass, it has a higher gravitational pull, but then just equally the other part of the mass is further away, so it has a much weaker pull. And so, like, overall, it just feels like it might not give you the result that you're looking for. So I'm not so convinced at this point.
And by massive objects and galaxy rotation.
But at the same time, I like the idea, because what the idea is saying is that, look, we have this unknown, we have this unexplained situation in our galaxies, most galaxies. And the only galaxies in which they don't occur are those in which the mass is not large enough to have relativistic effects, which I don't know how much of that is true or not true, because even a billion times the solar mass is pretty hefty. So, I mean, you know, looking at Wikipedia, it didn't say anything about the relativistic mass. It just said it was a smaller galaxy. And so at this stage, I'm kind of not convinced. It's just a proposed idea with no walkthrough, no theory that you can follow along and be like, oh, okay, it does match up. So I don't know.
Curves to study dark matter.
But again, it's fine to think about these things if they lead you to the process of putting together a model and putting things down like pen to paper and trying to create a model that answers this question. Because clearly what it's saying is that there's something beyond relativity. That's where our galaxies, that's what dark matter and dark energy are telling us, is that there's something beyond our current understanding of physics. And that's a big thing. That's not a little thing. So, I mean, a lot of mainstream academics, they get nervous about like science deniers. And so they try to present it as, no, we definitely understand. This is a small thing. So it's a very tight rope to walk. You know, on one hand, you don't want to encourage science deniers by saying like, yeah, no, it's a big thing. We don't know, you know. But on the other hand, you do want to encourage scientists to think big and be like, hey, we really don't know. It could be a whole different paradigm. So it's a tightrope.
Dark matter is essential for explaining the large-scale structure of the universe, the formation of galaxies, and how the universe evolved. Without dark matter, our current understanding of cosmology would be incomplete. Relativistic mass, on the other hand, comes from Einstein's theory of special relativity and refers to how the mass of an object appears to increase as its speed approaches the speed of light. This phenomenon is connected to time dilation and length contraction.
This is not true. Again, what I really like about the Fermilab explanation is that it's the momentum that is increasing. The mass, like, maybe it does, maybe it doesn't, but
Effects that occur when an object moves at a significant fraction of the speed of light. As an object's velocity increases,
and again, it's a separate question of what's going on with the fabric of reality. Why does the momentum increase? I don't know.
the energy required to accelerate it further also increases. This added energy contributes to what is known as the relativistic mass. The faster the object moves, the more massive it becomes at the speed of light. This mass would become infinite, which is why, according to relativity, no object with mass can reach the speed of light. Relativistic mass is a concept mostly used in high-energy physics, such as when dealing with
Infinite momentum. What we know is that it'll be infinite momentum. So conflating mass like in this video is a bit premature and not very sound science. So if he had said, like, according to some, or according to our proposal, we conflate the two, and therefore, that would be fine. But this is stating a proposal as a reality, and that's not good science.
particles and particle accelerators that move at speeds close to the speed of light. It's important to note that modern physics prefers to emphasize rest mass, the intrinsic mass of an object at rest, rather than relativistic mass, focusing instead on energy through Einstein's famous equation. Key differences. Nature. Dark matter is thought to be a form of matter made of unknown particles that interacts weakly with normal matter and light, whereas relativistic...
That's one of the theories. Dark matter is essentially a proposal that, that's what dark matter is. You plug it into the equations, you plug this dark matter into the equations, and you get the expected results, but we don't know what it is. And so it's kind of similar to Max Planck and quantizing black body radiation, where you do it to see if it works, it does work, and then you sit back and you're like, what does this mean, right? So that's kind of where we are at with astrophysics and cosmology. Is you plug the numbers in and you're like, yeah, it fits, but what does it mean? So we don't know what it means.
mass is a phenomenon that occurs due to the...
And one of the theories is that it could mean that there are these things. They're not saying it's definitely the solution, but they're saying it could be.
increase in energy as an object moves faster.
Or it could be that, that the answer is both of them, or somewhere in between, that when you do have such large masses, it does do something funky to space-time. And that results in what we get with the rotation of the galaxies. But how do you do an experiment? How do you differentiate the two?
Detection. Dark matter is detected indirectly through its gravitational effects on galaxies, stars, and light. Relativistic mass is calculated when studying objects moving at high speeds. Role in physics.
What?
Dark matter plays a crucial role in cosmology, explaining galaxy formation and the structure of the universe. Relativistic mass is important in high-energy physics, especially in understanding particle behavior at speeds close to the speed of light. Behavior. Dark matter behavior.
Again, not quantifying, not qualifying it, sorry. In particle physics, you just blah, give us an example of what you're talking about. And I don't think that is correct. I don't think relativistic mass plays any role in particle physics. I don't think so.
Behaves like a mysterious mass that doesn't interact electromagnetically, while relativistic mass refers to the apparent increase in mass with speed. In conclusion, while both dark matter and
Well, with the definite increase in momentum and apparent potential increase in mass, or the mass could be exactly the same, and what you're just seeing is some relativistic effect, which makes the momentum appear to be larger than it is, because I don't know, maybe it's tearing through space-time. If you go that fast, maybe it's turbulence in the fabric of reality itself. Like,
And relativistic mass involve mass and gravity. They arise from entirely different physical phenomena. Dark matter helps explain the structure and behavior
which again, if it is turbulence, how would that increase your gravitational waves or pull? It's not one-to-one here.
of the universe, whereas relativistic mass is a result of high-speed motion in the context of special relativity. Thanks for watching.
Yeah, I'm not so convinced. I mean, there needs to be a more detailed video with more qualifying examples of some of these broad statements.